This is Navi 48, AMD's first RDNA4 based GPU. It powers the new RX 9070 and 9070 XT. But there's something strange going on with this chip. And no, I don't mean the odd looking rectangular shape of the die. To show you what I mean, we have to compare it to the competition. Nvidia's Blackwell generation GB203, the chip that powers both RTX 5080 and 5070 Ti, packs 45.6 billion transistors into a die size of 378 square millimeters. That's a very respectable transistor density of 120.6 million transistors per square millimeter. At only 356.5 square millimeters, Navi 48 is a bit smaller than GB203, but at the same time, it contains 53.9 billion transistors. Navi 48 is 6% smaller, but has over 18% more transistors. That's a 25% increase in transistor density, a massive difference for semiconductors where every square millimeter counts. 25% is getting close to what we expect from a new process node nowadays. What's going on here? Is Navi 48 using a different process node? No. Both Navi 48 and GB203 are based on TSMC's 5nm class. Blackwell uses 4N, which is most likely a Nvidia specific version of N5P, and Navi 48 uses the slightly newer N4P. Both are improved variants of the original 5nm node. According to TSMC, N4P can be up to 6% denser than the vanilla N5, but neither is Nvidia using the vanilla node, nor does it explain the 25% advantage that AMD achieved. Of course, the process node is only one aspect affecting transistor density. The use of high performance versus high density cells also impacts density, and so does the specific mix of logic, cache, and analog areas on a chip. But GB203 and Navi 48 are very much comparable in these areas. Both are GPU designs with a high clock speed, both have a 256-bit memory interface and 16 lanes of PCI Express Gen 5. They even have similar cache sizes with 64 MB L2 cache on GB203 and 64 MB Infinity Cache plus 8 MB L2 cache on Navi 48. Still, Navi 48 is 25% denser. I usually don't need a specific reason for a chip deep dive, but AMD using some kind of magic sauce makes Navi 48 even more interesting. Let's take a closer look at Navi 48 on a silicon level, check out AMD's new RDNA4 architecture, discover interesting changes to AMD's Tensor Cores, and compare it to Nvidia's GB203. Maybe we can figure out AMD's secret on the way. Before we look at the silicon itself, let's see what we are actually looking for. Luckily for us, AMD created a block diagram which shows a fully enabled Navi 48. The largest part of the GPU is the 4 shader engines. Each shader engine contains 8 dual compute units, a rasterizer, a primitive unit, and 4 parts marked RB+, which are the render output units or ROPs for short. In between the 4 shader engines, we can find the geometry and command processors, 2 blocks labeled ACE, and 1 block each labeled HWS and DMA. ACE is short for asynchronous compute engines, which dispatch the incoming commands to the compute units. HWS should be short for hardware accelerated scheduling, taking over some of the scheduling work from the CPU. And DMA is short for direct memory access, which AMD likes to call smart access memory, better known as rebar. There are also 2 parts of L2 cache, each containing 4 MB of SRAM. One of the little L2 squares equals 256 kilobytes. To the left and right of the shader engines, we can see the memory system with memory controllers and AMD's Infinity Cache. Navi 48 has a 256-bit interface and 64 MB of Infinity Cache. And last but not least, we can see PCI Express Gen 5, a multimedia and a display engine on the bottom of the schematic. All of this is interconnected by AMD's Infinity Fabric protocol. Even though I would have loved to see AMD connect 2 Navi 48 chiplets, that's not what the Infinity Fabric does indicate in this context. Now that we know the basic layout of Navi 48, let's take a look at the silicon and see how close to reality the block diagram actually is. AMD released images showing the chip as a sort of die shot. Looking at it, I'd say it's definitely based on a real image, but most likely artistically altered in certain ways, much like the chip images Apple used to release, which they sadly stopped with the M4 series. We might not have the amazing resolution we are used to when analyzing die shots from Fritzchen's Fritz, but it's good enough to work with. If you watched my chip deep dives before, you know that I like to start my analysis at the edges of a chip. That's where we usually find all the interconnects that have to communicate with the outside, like the memory interface, PCI Express, and so on. And it's not different here. Bottom right, we can find the PCI Express physical layer. AMD implemented PCI Express 5.0 with 16 physical lanes. If we look at the placement of Navi 48 on a PCB, we can see how close it's located to the PCI Express slot of the card. That's because Gen 5 is more problematic in terms of signal integrity, and one solution is to reduce the physical distance. I actually like AMD's no-nonsense approach. Just place the chip as close to the PCI Express slot as possible. To the left of the PCI Express PHYs, we can find 4 display PHYs, used for the up to 4 display outputs on a Radeon RX 9070 series GPU. Next up is the memory interface. Navi 48 has a 256-bit memory bus divided into 8 32-bit clusters, which are further subdivided into 2 16-bit PHYs. 3 of these 32-bit clusters are located on the left and right core lines of the chip, and 2 more are on the very top. If we zoom out to the PCB level again, we can see that the location of the memory PHYs perfectly matches with the placement of the GDDR6 memory chips. 6 chips left and right and 2 above. Each memory chip is connected via 2 16-bit PHYs. Now that we've located the memory interface, let's look for the infinity cache. We know it has to be in close proximity to the memory interface, and there should be 64 megabytes in total. Starting at the top, we can locate 2 symmetrical blocks of cache right below the top left and right memory PHYs. The resolution isn't that great, but both areas should contain 8 megabytes of SRAM. Going further down, there are 2 symmetrical rows of cache left and right. If I counted correctly, both cache rows contain 18 megabytes of infinity cache each. Now it gets a bit weird. There are 2 tiny SRAM blocks nested in between the memory PHYs. These blocks only hold 2 megabytes each, but are still symmetrical for the left and right side. Going all the way down to the bottom of the chip, the symmetry stops. There are 2 additional 4 megabyte blocks, but this time with different shapes and slightly different locations. It's an interesting layout for sure. AMD uses different SRAM cluster sizes with 2, 4, 8 and 18 megabytes. But it still adds up. There's a total of 64 megabyte infinity cache on Navi 48. AMD forgoes symmetry when it results in a better use of space. Since we are already talking about cache, let's stay on topic and locate the L2 cache. According to the schematic, there should be 8 megabytes somewhat in the center between the shader engines. And yes, the L2 cache is indeed located in the center of the chip. There are 2 mirrored areas, each containing 4 megabytes of SRAM, for a total of 8 megabytes. With RDNA4, AMD increased the L2 cache per shader engine to 2 megabytes, while previous RDNA versions only had 1 megabyte per shader engine. That's why Navi 48 with 4 shader engines has 8 megabytes L2 cache, while Navi 31 with 6 shader engines has only 6 megabytes. Right next to the L2 cache we can find the memory controllers. It's hard to see, but each area contains 8 16-bit controllers for a total of 16 16-bit memory controllers, perfectly matched with these 16 16-bit memory PHYs. The whole memory system is interconnected. The memory PHYs are used for the physical connection to the memory chips. They basically power the wires that are routed over the PCB to the memory chips. The memory controllers are telling the memory PHYs what to do, and the infinity cache tries to predict what data from the memory will be needed next and tries to preload it. So once the actual memory request comes in, the data is hopefully already in the infinity cache, and the compute units don't have to wait for a lengthy physical memory access. Interestingly, RDNA4 did get rid of the L1 cache. Instead, RDNA4 seems to use a kind of buffer. If we look at previous RDNA architectures, all shader engines had a shared L1 cache. This changes with RDNA4. The most likely explanation is that with the introduction and constant iterations of the infinity cache, the L1 cache didn't offer the same benefits as before. Adding too many cache levels into the cache hierarchy can negatively impact performance and latency. Lastly, the command area of the GPU is in the very center, right between the 2 L2 cache clusters. At least that's where I would place it, and that's how I have labeled it. But enough about memory systems and cache. Let's tackle the area where the real work is being done, the shader engines. Navi 48 has 4 shader engines, and they are easy to spot. Just like in the block diagram, 2 are above and 2 below the L2 cache and command area in the middle. Combined, they take up a major part of the entire die. Let's zoom in and see how a single shader engine is constructed. A shader engine has 8 dual compute units, which AMD also calls workgroups, and a single raster engine. As the name implies, each dual compute engine contains, you guessed it, 2 compute units. A compute unit is basically the equivalent to what Nvidia calls streaming multiprocessor or SM. Even though the resolution of the image isn't great, if we trace the repeating patterns, we can place the 8 dual compute units or workgroups. The raster engine is located below the compute units. We can see 4 distinct clusters of render output units, each with 8 ROPs, and a larger area most likely used for the rasterizer and the primitive unit. As such, each shader engine has 32 ROPs, and with 4 shader engines, Navi 48 has a total of 128 ROPs. Due to the resolution, it's impossible to actually label individual areas inside of each dual compute unit. But AMD shared a detailed schematic of the inner workings, so let's take a look at that. To start, it's important to know that these diagrams are a simplified representation of how such a complex system as a compute unit or workgroup functions. Not everything you see here has the same physical representation. The dual CU is divided into 2 compute units, one shown on top and the other one below. As you can see, some of the resources, namely the cache, is shared between both compute units. This increases area efficiency. The most important part of a compute unit is the arithmetic logic units, or ALUs for short. These are also called shaders or stream processors, and Nvidia likes to call them CUDA cores. RDNA4 has 2 types of vector ALUs, one that can do floating point and integer operations, and one that can only do floating point. These are labeled as 32 FMA ALUs and 32 FMA/int ALUs. At least that's what the block diagram says. Things might not be as they seem, but in-depth GPU architecture analysis is beyond my scope of expertise. A compute unit also has 8 TLUs, a so-called AI accelerator, more on that later, and a scalar unit. The scalar unit and the vector units each have their own general purpose registers or GPRs, which is basically a very small and fast cache. But wait, if this diagram shows 2 compute units, why are there 4 blocks containing the same logic? That's the dual issue shaders AMD introduced back with RDNA 3. If we count all the vector ALUs in a dual compute unit, according to this schematic, there's a total of 256 shaders. And since each shader engine has 8 dual CUs, that's 2048 shaders per shader engine. And with 4 shader engines, Navi 48 should have 8192 shaders. But if we check AMD's website, the RX 9070 XT only has 4096. The best way to explain it is that just like both compute units in a dual compute unit share some of the resources, the same is happening within each CU. In theory, RDNA 3 and RDNA 4 have the ability to utilize more than 4096 ALUs, but only under certain circumstances. I'm not a GPU architecture guy, and all of this makes my head hurt, but the best comparison would be something like SMT or Intel's hyperthreading, where each CPU core can handle more than just one thread. These implementations do include extra transistors, but it's not like there are 2 full cores. That's why AMD states that the RX 9070 XT has 4096 shaders, but the GPU block diagrams show twice that. As you see, nothing is as it seems, and the deeper we go into the architecture and silicon, the more complicated it gets. That's why we stop here. For more details, I can always recommend Chips and Cheese. George knows a lot more than me about architecture, and he has some great articles and videos on RDNA 4. That's especially true for another big part of the compute unit, the so-called AI accelerator. Starting with Turing, Nvidia implemented Tensor Cores into their GPU architecture. Tensor Cores are basically fixed function hardware that excel at multiplying matrices, which is what you do when computing machine learning algorithms. It's not like this can't be done on the vector LUs. They're really good at that too, but just not as good and as efficient as a Tensor Core. With RDNA 3, AMD started to implement AI accelerators into their architecture, but it was a different concept. Instead of Tensor Cores, AMD used so-called wave matrix multiply accumulate instructions to accelerate the computation of matrix multiply accumulate operations on the vector ALUs. This does require additional transistors, but less than implementing Tensor Cores. It's a smart solution which enables the existing ALUs to execute machine learning operations much faster. But it's not dedicated hardware, at least not in the sense of Nvidia's Tensor Cores. This has changed with RDNA 4. Navi 48 does use unique Tensor Core transistors, which results in a massive performance boost over RDNA 3. This means RDNA 4 can compute double to quadruple the number of AI operations compared to RDNA 3. Not only that, AMD's new Tensor Cores support new math formats such as BF8 and FP8, which is used for the FSR4 AI-based upscaling. That's the reason why RDNA3 might not support FSR4. First, because it doesn't even support the FP8 format, and second, because it lacks dedicated tensor cores. This comparison from AMD also shows that integer formats such as int8 and int4 see the largest performance gain, which makes sense because, as we just learned, out of the 64 ALUs in a compute unit, only 32 can do FMA and int, while all 64 can do FMA, at least in theory, which means using dedicated tensor core transistors over the ALUs provides a larger gain for integer operations, as they are now just as fast as floating point operations. AMD also implemented the ability to use sparse data values, which can double the performance by reducing precision, which results in up to 8 times the ops of RDNA3. A massive generational leap. I've talked to a couple of smart people regarding the question if RDNA4 has tensor cores or still uses WMMA on vector ALUs like RDNA3 did, and I've asked AMD. In the end, it's pretty obvious that AMD did spend extra transistors on tensor cores for RDNA4, and AMD confirmed the additional tensor core transistors. Thanks again to Cheese and Carbon Cry for being very patient and answering my questions. But it's always important to keep in mind that we are still talking about very tightly integrated blocks of transistors. Most people would agree that Nvidia has dedicated tensor cores, but they are still part of ASM and rely on cache and register file bandwidth, on getting the right commands at the right time, and much more. Even on Nvidia's GPUs, running a calculation on a tensor core does block ALU calculations of that SM subpartition for at least for a certain clock cycle. The same is true for AMD's RDNA4 implementation. The tensor cores are not completely separated hardware units. They are part of the compute unit. Using them for matrix multiply accumulate is much faster and more efficient. But it doesn't mean that you can utilize all ALUs and tensor cores at the same time. And then there's the implication of AMD's dual issue approach. Navi 48 has dedicated tensor core transistors, but depending on how we read the block diagram, it could be 2 or 4 per dual compute unit, and thus 16 or 32 per shader engine, and 64 or 128 in total. I'll go with 64, since AMD also officially says there are 4096 shaders. So yes, Navi 48 does have 64 tensor cores. Spending extra transistors on tensor cores might be one of the biggest changes in RDNA4 and finally allows AMD to compete with Nvidia's AI performance. I'm very happy to see that, but enough with AI and tensor cores. Let's talk about the other current hot topic, ray tracing. And similar to AI, RDNA4 also introduces drastic changes over RDNA3. Compared to RDNA3, RDNA4 literally doubles the ray box and ray triangle units from 4 and 1 to 8 and 2. The BVH processing still runs on the shaders, but RDNA4 introduces a new BVH8 structure which reduces traversal time and memory usage. And a new technology, AMD calls it oriented bounding boxes, optimizes BVH traversal performance on real-world geometry. There are many more aspects related to ray tracing performance. For example, the new out-of-order memory access, which also improves RT performance. There's a great article over at Chips and Cheese. I can't seem to stop talking about them in this video, but I promise George didn't pay me. It's interesting to compare the different RT implementations between Intel, Nvidia and AMD. Just looking at the basic number of ray intersections, Intel's Alchemist can do 12 ray box and 1 ray triangle per cycle. Battlemage improved that to 18 ray box and 2 ray triangle. As you can see, Intel is heavy on ray box with a 9:1 ratio. AMD's first RT implementation on RDNA2 started with 4 ray box or 1 ray triangle per cycle. RDNA3 didn't really change that and improved RT by improving latency and bandwidth and just having more compute units and thus more RT cores. RDNA4 actually upgrades the ray accelerators for the first time and now does 8 ray box and 2 ray triangles per cycle. That's a 4:1 ratio. Nvidia is pretty tight-lipped on their actual implementation. Ampere could do 2 ray triangle tests per cycle and both Ada Lovelace and Blackwell doubled that. This means Blackwell can do 8 ray triangles per cycle. I couldn't find verified numbers for ray box though. There's a very commonly cited ray tracing hardware tier list, but I think it might be time to toss this concept aside, because it very obviously describes a progression that is focused on Nvidia and doesn't seem to be related to actual performance, but to a perceived idea of what the best hardware implementation looks like. Which makes sense because Nvidia is at the forefront of ray tracing And what else would you build your tier list on? But according to this list, RDNA4 is still only a level 2 GPU, same as RDNA2 and RDNA3, even though it greatly improved RT performance and introduced novel features. Time for a new definition in my opinion. I'm all for a more real-world focused approach. Best way would be to test how much of an FPS hit an architecture takes when turning on ray tracing. More than 50% is tier 1. Between 30 and 50% is tier 2. Between 20% and 30% is tier 3. Less than 20% tier 4. And finally, less than 10% is tier 5. But that's just an idea. Now that we've discussed the most important changes inside each dual compute unit, let's zoom out again. With the shader engines finished, we have labeled all major parts of Navi 48. There are still some unmarked areas in the center around the L2 cache and at the bottom below the shader engines number 3 and 4. The unmarked areas in the center contain the asynchronous compute engines, the hardware accelerated scheduling, and direct memory access logic. But I'm not able to tell the exact locations. The area on the bottom contains control logic for the display and PCI Express interfaces and AMD's new media and display engines. Same thing here, I can't tell you the exact locations of these parts. To put some perspective to our analysis, let's take some measurements and compare Navi 48 to Nvidia's GB203. Each RDNA4 shader engine is about 33.64 square millimeters in size, which is 9.4% of the Navi 48 die. All 4 Accelerators engines combined take up 37.8% of Navi 48. The Infinity cache, split up into many separated areas, comes to a total of 52.55 square millimeters, or about 14.7% of the die. Though this measurement is pretty rough, and I think it might be less than that. The resolution just isn't that great. The 256-bit memory interface consists of 8 blocks with 5.74 square millimeters each. That's a combined area of 45.92 square millimeters and about 12.9% of the chip. And the PCI Express 5.0 PHYs take up 5.39 square millimeters or 1.5% of the die. Nvidia's closest competition to Navi 48, GB203, offers an interesting comparison. Here's a quick overview of GB203. If you are interested in an in-depth analysis of Nvidia's Blackwell, check out my RTX 5090 deep dive video. Nvidia uses GDDR7 memory. GB203 has 8 32-bit PHYs, each about 13 square millimeters in size, for a total of 52 square millimeters or 13.8% of the chip. That's only slightly larger than the memory interface on Navi 48. It's impossible to say if Navi 48 also supports GDDR7. I think it's unlikely, but there isn't much size difference between the memory PHYs. The same is true for the PCI Express 5.0 implementation. Nvidia uses about 5.93 square millimeters or 1.6% of GB203, almost the same area as on Navi 48. The cache is also very close. 64 megabytes on Navi 48 used 52.55 square millimeters, while 64 megabytes on GB203 used 49 square millimeters or 13% of the chip. But keep in mind that my Navi 48 measurements are most likely on the larger side. What's interesting though is the GPCs, which is Nvidia's version of AMD's shader engines. They are a bit smaller, so there's 7 GPCs on GB203. Each GPC uses about 24.7 square millimeters or 6.5% of the die. Combined, all 7 GPCs take up 172.9 square millimeters or 45.7% of the chip. That's quite a bit more than the 37.8% the shader engines take up on Navi 48. But then the command and control area in the middle of Navi 48 is larger than Nvidia's, which indicates that Nvidia has included more functionality in each GPC, and for a one-to-one comparison, we would have to add some of that center area, minus L2 cache and memory controllers, into the calculation. It just shows that it's impossible to directly compare different architectures. But at the same time, it's interesting how close some of the area usage is. Memory interface, PCI Express PHYs, and cache are all very close across these two very different architectures. So how do we explain the 25% density advantage of Navi 48 we've talked about at the start of the video? What's AMD's magic sauce? GB203 with the same 151 million transistors per square millimeter density as Navi 48 would only be 302 square millimeters in size, a reduction by 76 square millimeters, which is more than an entire Zen 5 CCD. And Navi 48 with Nvidia's lower 120.6 million transistors per square millimeter density would be a massive 447 square millimeters chip. To be honest, it's almost impossible to figure out with the limited information we have. Navi 48 has slightly more on-die cache, which usually increases density. But aside from that, it's down to the specific usage of high density versus high performance cells and how much work the design teams put into optimizing for area over other aspects. I'm sorry to say, but unless AMD tells us, we can't figure out AMD's secret sauce. At least not now. RDNA4 is a massive step forward for AMD. It's the biggest architectural overhaul since the introduction of the original RDNA architecture and improves the GPU design in key areas. The most important changes are the introduction of dedicated Tensor Core transistors, the massive upgrades to the array accelerators, and the long overdue changes to the cache and memory system. With RDNA4, AMD finally has an up-to-date architecture that can rival Nvidia in terms of capabilities. The crazy part is that AMD didn't even design a high-end chip this time. Navi 48 is a mid-range GPU with only 64 compute units. Navi 31 on the 7900 XTX not only has 96 compute units, that's 50% more, but also a 50% wider memory interface and 50% more VRAM. But each RDNA4 compute unit is so much faster than a RDNA3 compute unit that the 9070 XT is able to compete with a 7900 XTX in raster workloads and easily surpasses it in ray tracing and machine learning workloads. It's the same situation again we saw with the first RDNA generation. Navi 10 was also a mid-range GPU, but it did compete very well against Nvidia's RTX 2060 and 2070. So much so that Nvidia was forced to release the RTX 20 Super refresh cards. Maybe we'll see the same this time around. One can only imagine how a RDNA4 GPU with 6 shader engines would perform. And the cool part is that such a card wouldn't even need a wider memory interface. With a GDDR7 memory system, AMD could use 30 GB per second, 3 GB GDDR7 modules, and increase both memory bandwidth and size by 50% while sticking to the same 256-bit interface, which would pair perfectly with a 50% increase in shader engines. Such a chip would only be about 35 to 40% larger in die size and offer a similar increase in performance, placing it firmly ahead a RTX 4090 and not that far behind a 5090. And with a slim 256-bit interface, the TDP shouldn't exceed 450 watts. But this is just me dreaming. There's very little chance we will see a larger RDNA4 based chip. It takes about a year from tape out until a product hits the shelves. And even if AMD already started with the design, it would take at least until the second half of 2026. Which is when we might start to see the first UDNA-based GPUs. But we don't need a high-end RDNA4 chip. Navi 48 is more than enough. All it took was one subpar generational uplift from Nvidia and one great one from AMD to mix the cards again. And we know how much the GPU market desperately needs more competition. RDNA4 definitely came at the right time. I hope you found this video interesting and see you in the next one.